if you done your conclusions based on summary, but then you had to mention that the covariates are one-dimensional. Okay, for instance, it's still possible to use summary even if there is a factor, but if this factor has only two levels, then you're fine. Then it's also as good as ANOVA, because you're just comparing two coefficients with each other, all right, in a factor. So whether they're the same or not, and basically you see in the ANOVA one, if you have to mention that they're all, and you have to mention that you're totally fine. There's anyway, if you use ANOVA, okay, if you use ANOVA, there is no mistake whatsoever. Summary, then it's only possible, of course, if all the degrees of freedom once, then summary is good if you didn't mention the fraction. Okay. Okay, I hope that's clear. Okay, let's start with today's lecture. Let me share the screen. So we start with the let's see, first lecture, the end of the course. Actually, I think it's actually very good that we're with the other style of courses, when courses are very compact and they're very intensive. In a way, it's kind of good that you just can tell a lot of material in a short time, but I think the information, to let it sort of settle down for some reason, I just compare this with the, my son is now following this study in Delft, and they have this mathematics course there, which is just very intensive. There's a huge amount of information in a very short time. He's just not absorbing it. It's just okay. This is just a side thing. Anyway, let's go on. What we did is we just moving from very specific models, linear model. Okay, everything was very, very rigid there, the very rigid structure. So this linear function additive model was normal. Okay, then we said, okay, let's drop something at least of this. We drop the linearity, and then we allowed function to be nonlinear. We also allowed allowed that error is not normal anymore. It was the second topic. We dropped additive structure, okay, but we still kept a very, very important assumption, namely the assumption of independence, of very essential. So basically, we can think of the experiments like, okay, there is the same thing, the same phenomenon happens, and it's independent of everything which happened before or after. We don't even have the notion of before or after, right? There's no time there because it just happens. So for us, observations have no time. They do not be ordered. That's not a problem for us. Because they're collected under the same conditions, we say they're independent. And that's very, very important because there's a lot of structure in that. So we are going to drop that, okay? This really makes all the tools we did so far, well, not completely useless, right? But much of it is going to be just useless. So we cannot use it once we drop independence. And this is what we're going to do. General object principle. So we just observe a whole bunch of random variables. That's it. And we don't assume anything about them. They just, whatever they are. In fact, they are in many yeah, it's sort of, well, we don't know whether dependent or not. And then we just record the annual flow for a number of years, and we just collect this, and we have this picture, okay? So what can we say? Well, we cannot say they're independent, for sure. That's it. Okay, what is the index observation? And then another observation that was just two distinct, different observations from each other, but now it's going to play a role over time, appearing in time. And then, okay, whatever the time unit is, it's like a fixed time unit, for instance, a second or a day or a year, okay? And then we label that each observation according to that time unit, okay? And then it doesn't necessarily start from 0. It could start from 0. It could start from -10. It depends on the scale we use. And in fact, we can allow even go in the past, in the infinite past. That's no problem, at least theoretically. So time runs from -infinity to +infinity. This is for theoretical purposes, at least. Okay, here's another one. That one for sure, here we cannot say they're independent. Absolutely not, okay? So this is just the prices of some stock indices, basically, and it evolves, okay? And it evolves, and of course, it depends on what was before, right? And of course, they're also dependent from each other, okay? So these are different stocks, and then you see they're all grow, and then they're all and absolutely. So this nobody can deny that. So all these models with independent random variables, they're sort of not based on independence. All right. Okay. There are actually two ways to go, basically. Well, many sort of move in two directions. So what do we need to do? And what is it that we can do? Well, of course, if you don't assume anything, then nothing you can infer. So there's just no way you can do any inference. So you still need some structure. Okay, you drop independence. That's fine, but then if you don't assume anything at all, then there is no way you can do any useful thing. So you have to sort of assume a certain structure. You have to sort of to make it kind of something you can work with. Otherwise, you cannot just work. So there's just x's, and then what? There is nothing. You have to. And there is one very simple assumption on one hand. On the other hand, it sort of leads to very rich theory. Okay, so this is stationarity. We are going to walk this way a little bit, not far away. This is a very big field. In fact, this field is very important for engineers. Okay, these engineers, they're very much fond of that, especially in this field when you're sort of transmission of signals and then processing of signals, all kinds of signals, you know, in this electricity and this radio thing and so on and so on and so on. So they use this field very extensively in those, and for instance, there are big, sort of very important courses in technical universities where they study only that, nothing else. Okay, so it's just we'll touch upon that. We're not going to go deep, but I will, at the end of this lecture, I will sort of mention the most important things, although they're not in the lecture notes, but I still include them in this course. And they're not part of the exam, but they're part of the assignment, okay? So at least to make you sort of, to get you familiar with this topic, okay? At least up to some degree, not very deeply though, but still to get a flavor of what it is. Okay, what is stationarity? It's basically pretty simple. So you just take a time series, which is just an arbitrary bunch of random variables, and you sort of order them in time. They arrive in time, you think they arrive in time. And then what we are going to assume, we are going to assume that it's sort of the distribution of, so we just take two random variables, one at time observed at time point t, another one observed in time point t plus h, okay? And then we sort of assume that the relation between these two, the covariance between these two stays the same as long as the time lag is the same. So if we move, it's like, it's always t and t plus h, and we let t vary, but we keep the time lag, okay? So there is t and xt and xt plus h, and there is a fixed time lag between these two, and we move it around like this, then the covariance stays the same, okay? This is what we require. So that that's why they're called stationary, okay? So there's sort of the same relation between these two. There is strict relation, stationarity and weak stationarity. We will work only with weak one, so we just, therefore I dropped this word weakly. And it's only about correlation, okay? So it's just, we are not talking about distributions, only correlation between these two. Okay, what do we require? We require that expectation of this time series is the same all the time, okay? It just stays the same. So it's just, there is something which is stable, the expectation is stable, and it sort of moves around it, okay? So xt moves around it, but it's always distributed around the same expectation. And then we also assume that expectation of the product xt plus h is something which is independent on t. It depends only on h, only on lag. Okay, if we assume this, then you say, well, what about correlation? It's the same actually as saying that covariance between these two depends only on t, on h. Why is that? Well, because covariance is equal to expectation of the product minus expectation times expectation. Since we assume that expectation is the same, so here we have mu, then of course, assuming that this quantity depends only on h, it's the same, it's equivalent as saying that the covariance between xt and xt plus h depends only on h, it doesn't depend on t. So this is equivalent thing. So, okay. That's it. Basically, that's not much. Well, but it gives you a lot of, it actually led to very rich theory. Okay. Well, okay. So let us just write it down. It's covariance function. Covariance function of stationary time series. So it's a covariance between xt and xt plus h. So this is just this by definition of the covariance. We see that it depends only on h, so t is not involved there. So it's a function of only one variable, whereas in general it should be a function of two variables. And then that one is called autocovariance. Okay, why is that called auto? Because in principle, if it were covariance, then it would have been dependent on 2. But since it depends on only one variable, h, that's why, sort of, to make distinction between the general case and this particular case, people call it autocovariance function. Okay. Okay, what else can we say? Well, we can actually say quite a lot. First of all, notice that if we just put h equal to 0, then we have covariance xt, right? And that's its variance. So that thing must be positive. Okay, so that's function at point 0. Another interesting thing is that actually this function is, of course, is symmetric. You just simply, okay, what is the covariance between xt and xt plus h? It's the same as covariance between, you can call this as a u, say time moment u, then this time moment becomes u minus h, okay? And that's covariance function between u and u minus h, and that's gamma of minus h, and it must be the same, okay? So therefore it must be symmetric. Moreover, it has to be such a function which is always the absolute value is less than gamma of 0, less than variance. Okay, it could be negative, but it's never, absolute value is never bigger than the variance. Okay, why is that, by the way? Well, this is because of this Cauchy-Schwarz inequality. Anybody, if you haven't heard of this, this is just because of this. Okay, this expectation of x times y, and then you take absolute value and square, then it's always less than expectation of x squared times expectation of y squared. You can prove that. Should I go? I don't know. It's not so difficult to prove, by the way. Let me maybe give you. So it's a homework for you. Let me. Okay, it's a homework. So let's just, you need to prove that okay, let's just, the expectation of x, y, okay. Well, squared less or equal than expectation of x squared times expectation of y squared. Okay, let me give you, so you need to prove that. That's always true, okay? It's always true for any variables x and y. That's called Cauchy-Schwarz inequality, by the way. Okay, you could prove that as follows. You could take x, you divide it by expectation of x squared, and you take a square root of that thing, plus y divided by the same thing. Okay, square root here. Then you square that, and you take expectation of that. So this is expectation of something which is positive, so it must be like this, right? 0, it's bigger than 0, and then you work this out, okay? And then you do the same with the following, expectation of x divided by the square root of, like this, minus y, okay, divided by, maybe it's 2. Some people say, well, why do I need this? Well, you don't really, but that's good to know, actually. And then you work this out, and from here you should conclude that expectation of x, y is bigger or equal than minus square root of expectation x squared, expectation of y squared. And from here, you should conclude that expectation of x, y is less or equal than square root of that thing, okay? And that's exactly what you need, okay? From here, you should conclude this one, okay? Just work this out at home. It should be difficult. And you will see that this is always true. That's kind of amazing thing, isn't it? Anyway, we go back to, so make a screenshot if you want, and then work this out at home. And let me go back to this. So that's exactly this. And then if you instead of x, you use x minus expectation of x, then you can formulate this property for covariance, and this is just exactly from here. So the variance is gamma of 0, and that becomes covariance between xt and xt plus h, so it's gamma of h. So this is exactly covariance, less or equal than square root of the variance times variance, but variance is the same of both. Variance is actually constant. So therefore you get here gamma of 0, and it's positive, okay? So that you don't need to, so you take a square root of something which is positive, then you get the, you can draw the square root. Okay, what we can do, we can divide this function here by gamma of 0 to normalize it. And that what we were doing then, we are actually making an autocorrelation function. So what we are computing is the correlation of between xt and xt plus h. That function is called autocorrelation function. That function must depend on h only also, like covariance. And that function is nicer in a way that, first of all, rho of 0 is 1, because we just divided by gamma 0. And it's, of course, also asymmetric, and it's between -1 and 1. So that's a nice thing. So the covariance function could be anything. And if we normalize it, it's always between -1 and 1. So therefore, people always look at the autocorrelation function, because that function is sort of normalized. It's it has the same meaning as autocovariance function, but it's normalized, and it's always between -1 and 1, and therefore it's and the biggest value is rho of 0, because it's 1. So in the 0, it's the biggest value. It's 1. We know that, and everywhere else it's less than absolute value of 1. Okay, fine. Let's just go on. Let's just have a look at the examples of time series. Okay, let's just take a very basic one, and in fact, one of the most important ones. So we just take a bunch of random variables, and they're all independent. Actually, it doesn't need to, they don't need to be independent. It's enough to say they're uncorrelated. All of them, the covariance between any of different random variables is 0. That's enough. And they have the same variance, and they have expectation 0. Okay, so that thing called white noise, whatever that is, without specifying the distribution. Okay, you could think of normally distributed ones, but it doesn't have to be. So even not normally distributed, still white noise. It's still called white noise. It's as good as a normal one. And then let's just check, okay, what is this? So it's 0. What is the covariance? Well, covariance, it's everywhere 0 except in one point. Except in for h is equal to 0, then it becomes variance, and it's sigma squared. And everywhere else it's 0. So it doesn't depend on t. Okay, that's it. That's all we need. We all need the expectation doesn't depend on t, and covariance doesn't depend. That's it. We conclude immediately it's stationary. Okay, let's have a look at the other one. So you would think, oh, maybe all time series are stationary. No, of course not. Majority are not stationary. Okay, and then very simple one is a random walk. You simply sum those. You take white noise, and then you sum them all up. You just make it sort of Z0 plus Z1 plus Z2 plus Z3. And then that would be our so that's just cumulative white noise, basically. Okay, well, let's just check the first condition, expectation of xt. Well, it's 0, because expectation of each z is 0. So first requirement is fulfilled, no problem. But the second, it's not. So you simply compute this quantity, and you will see that it's equal to t sigma squared, because the t of them, and they're all independent. So then sum of t random variables, of independent random variables, variance of the sum is sum of the variances. So you have t of them, and then t appears here in the covariance. So it may not be stationary, because the covariance function depends on t. Okay? That's it. Immediately you conclude it's not stationary. Okay, let's take a more difficult one. Let's just use again this as a building block. actually, this white noise is very important. It's used as a building block for many, many others. In fact, many models in time series are based on this white noise. You start with white noise as a building block, and you build other time series like autoregressive and moving average. We will come to that. They all start with white noise, okay? And then we build on this. So what we're going to do, we just take white noise and make this new sequence of random variables. Half of ZT minus 2 ZT minus 1. Okay, this half here and this 2 here are arbitrary. Don't care about this. It's not important. Important is this linear combination of white noise. Okay. Okay, is it stationary? Well, take expectation of that. It's 0, no problem. Okay. Well, it's a bit of a difficulty to compute the covariance function. Okay, let's do that. Let's just compute covariance function. Here I need, okay, let me mention you, I hope everybody, so this kind of manipulation you will have to do in the exam, okay? You need to understand what the covariance function is, and you should be able to compute the covariances of linearly transformed random variables. Let me just show you just one, just properties of covariance. Okay, you need to know, because this is, I hope everybody knows, many of you know this. In case you don't, you really need to repeat this. So what is the, okay, so I need to remove this one. Oh. Okay, so covariance of between X and Y, what is that? So this is actually this, okay? Just definition of that. Okay, just take these two random variables and multiply them, and that's one definition. Equivalent definition is this. You just work this out and you see that this is the same. Okay. So this is, you could use either first one or the second. There's just the same thing. What you need to understand the following. You need to understand that the covariance, of course, between X and Y is the same as the covariance between Y and X. So it's just symmetric function. You just exchange them. There is no problem. And there is, okay, let me just do two properties. And another one is this. This is a very important one. Covariance of, say, let's say AX plus BY plus C, where A, B, C are constants. They're deterministic numbers. And then this new random variable is, we would like to compute the covariance of this random variable with some random variable Z. Then there is this linearity property which says it's just A covariance of X Z plus B covariance between Y and Z. Okay, and what about C? It's gone. That's the thing about the covariance. It sort of destroys all the constants. Constants are going to be gone. So that's it. This is the very important property. You need to use it over and over and over again. Okay, that property is just linearity property of covariance with respect to the each of the variables. So this is just with respect to this, and with respect to this, if you just exchange them, then you could use linearity on the other side as well. Okay, let me go back to, and if you just use this, okay, so it's just the properties of the covariance. What do I do? Somehow I don't see my stop share. Well. Okay, here it is. Okay, there it is. And then, okay, so what is it? So this is just covariance of between xt and xt plus h. Let me not be very, let me not compute this for a long time. Let me just say, you just put instead of xt its expression like this one, okay, just put it over here. Instead of xt plus h, you put its expression, right? That's just, instead of t, you put t plus h. And then you use this property, what I told you. So then it's just 4 terms, okay? 2 covariances. And then we know that ZT is uncorrelated, right? So then we look at all the possibilities, okay? Each is equal to 0, then we have 2 terms here which are not zeros, this term and that term. If h is equal to plus minus or minus plus 1 or minus 1, then we will get only 1 term here, which is 1 term is not 0. All the others are zeros, okay? And that term is going to be equal to that thing. And if h is bigger than 1, then all of them are 0, so they're all gone, okay? And then we can compute what they are, because we know that the sigma is equal to 4, so this variance is 4. We simply compute it here, so we will get that this function takes only 3 values, 17 minus 4 and 0. Okay, most of the time it's 0. Okay, it's only not 0 in 0. Okay, big number, 17. Plus 1 and minus 1, it's minus 4. You see it is symmetric as we think it should when it's stationary. And it depends only on h. It doesn't depend on t. You see that? That's it. We conclude it is stationary. This is what you need to do. Okay, so just this is a classical question on the exam. It will be again and again. So you're given a certain time series, you're asked, is it stationary or not? And you just need to check these 2 properties, expectation of xt is equal to something constant, and that the covariance function depends only on h and not on t. That's it. If it doesn't depend on h, that's it. You say stationary. If not, you say it's not stationary. This is very simple. Just check the definition of stationarity and conclude whether this sequence is stationary or not. All right. Okay. And there is another, okay, this is stationarity thing, okay, and we will come back to this. But let me just now mention the other direction which one can go. In fact, this is also a very big field, but that's a different kind of thing. We just forget about stationarity for now and say, well, let's just look at this and from the point of view of what we can do, okay? We have this linear regression, right? Maybe we can use it somehow. Let's just try to do something with time series by using the technique we've learned, okay? And that direction is also quite big, and it has to do with what one, okay, there might be some function mt, which is deterministic, which is inside xt, okay? This xt might have it as an ingredient, and it's deterministic and it's trend, okay? The expectation of xt might contain a trend, which is, and that drives the whole thing. So it is, of course, time series is always its expectation plus the rest. It's always true. But maybe that expectation is so big, which it drives actually the time series, the whole thing. And then it sort of wiggles around expectation, but this wiggling is very, very small. So basically the trend is actually determining the whole behavior. So that might be the case. So then we actually need to see what is this trend. Then the other thing is, which is very often the case in time series, in the real time series, the seasonal component. Something comes back, okay? There is behavior of time series and it sort of repeats itself. You see that this in a certain week in a certain day of the week, behavior of certain phenomena is the same, okay? Each Monday, something what you observe has the same pattern, and then it repeats, and then that means that part of this trend is actually kind of has a periodic component, and people call it seasonal component. We would like to sort of extract that component. We'd like to see what is that actually. Okay, that means that the expectation at the time point xt is equal to expectation of xt plus d, where d is the period of that thing. And usually you see that, but just by an eye, what the period is. Actually, if it's not known, then it's a very difficult problem to estimate. But you just see that by an eye, and in this course, we assume that D is known. So then we would like to see that seasonal component, and maybe we would like to extract that. And in principle, you can always write it down. You can always think of xt as some mt plus st plus the rest. It's always possible, right? So the question is, what is that rest, okay? So this is a trend, this is seasonal component, and this is the rest, okay, whatever that is. And hopefully, if we just subtract this trend and seasonal component, these are the things which actually sort of influence a lot and make this time series non-stationary, of course, because expectation non-stationary. If expectation changes with the time, then of course it's not stationary. That's it, forget it. So, but maybe if you extract trend and seasonal component, maybe the rest is stationary. And that's sort of a very good point to model, that you're just subtracting trend and seasonal component, you sort of go to the stationary thing. So this is the idea, okay? And then to this thing, we can apply this whole machinery for stationary process, because stationary process is a huge field. There's a lot of things like ARMA, ARIMA, and so on. All these models are based on the stationarity. You cannot do that if your time series is not stationary, but if you detrend and decisionalize it, hope the rest could be stationary, and then you can apply that, and you could combine these things. Okay, what about this seasonal component? The seasonal component is actually assumed to be sort of in such a way that the sum of all seasonal component within the period is zero, sort of that's centered. So we think of the seasonal component as expected variations from the trend. Okay, there's a trend, and there is sort of seasonal component which sort of wiggles around the trend, and it sort of cancels each other if you sum them all up over the whole. Why we are thinking that way? That sort of actually to make trend and seasonal component different from each other, because otherwise you cannot even distinguish between them. So at least this helps to sort of separate these two from each other. Otherwise, it's not identifiable problem to extract trend and seasonal component. You need to assume something about seasonal component to be able to extract it and not to confuse with the trend. Okay. Whatever estimator of seasonal component we get, suppose it's as tilde, we can always center it. Okay, it's always possible. We simply take an average over the period and subtract it from each value of the estimator of seasonal component, and then it's centered, because if you take sum of this, it's going to be zero. So it's always possible to center. All right, let's have a look. What is white noise, for instance? Well, white noise is this. There's just no pattern. It just wiggles around zero. That's it. This is what we see. All right, what else? Okay, now it's a true data. So this is the time plot of United States population, and of course it grows, right? So it's been growing all the time, and you see here a small sort of cusp, something sort of small irregularity in the pattern, which has to do with the Second World War, I guess. But anyway, you see there is a trend here, apparently. So you cannot say it's stationary, absolutely not. There is a trend here. So this is very relevant problem to extract the trend here, okay? All right. Another thing is, I find this weird data set, if you just think about it. So this is just accidental death, okay? So these are accidental death recorded in the United States from 1973 to 1978. And then, and it has a period of 12 months. You just see that, see its sort of behavior. So there's always a maximum in July, okay? So accidental death, can you imagine that? So it's just something very, very random, but it has periodicity. It behaves like this. It's weird, really weird. So there is a small annual spike in October each time, and there is small minimum each year in February. Okay, but it has to do with, apparently it has to do with the fact that people are outside more in July, right? And they're more inside in February, I guess. But still, it's curious. So then there is a seasonal component here, right? We would like to extract that. And maybe also a trend, which we do not see because seasonal component is sort of prevailing here. All right, let's go on and see trend estimation. How can we estimate trend estimation? Okay, there are two types of approaches, like global and local, which is relative division. So don't pay too much attention to it, but people think that way. And for instance, we would like to use our technique we already know, right? This linear regression, for instance. So we assume that there is a trend MT, and we can model it as some parametric function. Okay, think of for instance, quadratic polynomial. We can describe it by three parameters: beta 0, beta 1, and beta 2. Okay, and then we would like to sort of fit that model. Okay, of course. It's not linear regression, but we pretend as if it were a linear regression. And then, of course, we can compute this beta hat, beta 1 hat, beta 0 hat, beta 1 hat, beta 2 hat, just by minimizing the residual sum of squares. And that would be our estimator for a trend. Why not? So that's a global one because we use all the data. Okay, so it's used globally in a way. There is another approach, which is a kind of local thing. So what we do here is another idea. An idea is sort of make an average for estimating the trend at xt of xt. We make a sort of a window around this, like minus q time lags to the left plus q to the right. That would be, and then we average over those. Okay, that's it. Let's just take xt minus q plus 1, and so on, up to there is xt here in the middle. Okay, we take minus q plus q time lag, time span, and we average over that, and that would be our estimate. And then we move it. Okay, if t changes, then of course this window will be moving to the left and to the right. Okay, and then we have to think what to do with the points at the very beginning and the points at the very end, because you will have to do something, because you don't have q points if you start with for x0, right? For x0, you have only q points on the right. You don't have q points on the left because there is no data there. So you'll have to do something there at the beginning and at the end. You have to figure out what to do. But otherwise, it gives you a very good method to do the estimation. Okay, and then what? And once you've done that, either way, okay, we can subtract it from our original time series, and that's called detrended time series. Okay, now let me just finish this thing, and then we'll have a break. Okay, that would be then detrended series. But if you sort of want to have your time series without trend, without estimating trend, then there is a very simple thing to do. It's called differencing. But of course, it has a disadvantage that you're removing it without estimating it. Here we estimated it, so we have something, okay, with this can sort of infer on the trend. But if you say, I don't care about trend, I just want it to be removed, then you could do this. This is very powerful technique. It's called differencing. You just apply differencing operator. You just take xt minus 1, okay? And then you get a new time series. It's called, and you can apply this operator many times, okay? And the thing is, if, for instance, you have a linear trend, a plus bt, by applying just one once this differencing operator, you will remove trend. Okay, the resulting time series will not have a trend. You can compute that. It's homework, and it's all done and also in lecture notes. So if you just compute what happens with the resulting time series, if you apply this operator, you will see that this is gone. It's not there anymore. Linear trend has been removed. And the thing is, that's very nice thing, is that if you take any polynomial, right, and you do this k times this operator, you will remove that trend as well. And you see, any function can be approximated by the polynomial. We know that. I mean, nice function, any nice function can be approximated by polynomial. So in principle, by applying this differencing operator, you can always remove the trend. So that's always possible, more or less. Well, again, there is a small problem here. You will have to decide what to do with the left and the right, okay? You will get time series which is going to be smaller, okay? Because you start with a big one, you take differences, and then there's, of course, there will be one which is not be available anymore because there's, and then you take differences. Your resulting time series is going to become smaller. But hopefully you have very long one, and then you don't really apply that often. That k is not too big. Okay, but then there's a disadvantage here. If you are interested in trend itself, you're not going to get it. You're just removing it, and you don't see it. So you removed it. That's a result of your operation, and you wouldn't be able to estimate that. Okay, let's have a break now for 15 minutes. From now on. Let me see how much time it is. Okay, we will start at 14:33. Okay, let's have a break for 15 minutes. And please go ahead and ask questions if you have any in the chat. I will have a look now. Okay. Okay, let us go on. Let us continue to our lecture. Let me share the screen. Okay, there it is. So we can remove this trend clear by applying this difference separator. But once again, if you're interested in the trend itself, that would be a waste in a way. It's exactly the problem. Often is the opposite. Actually, remove the noise and then go after the trend. So trend is the main, the object of the main interest, and one would like to eliminate the noise rather than. But here it's like removing the trend and sort of distilling the noise. Okay, this is what this difference operator does. Okay, let us look at the particular procedure. Okay, let's imagine that we have time series xt, which we observe, and suppose we see that there is a trend and there is seasonability there. What can we do? Okay, so here's the procedure which is which can be applied. So first of all, we would like to estimate the trend, and let's do that by this second approach. Okay, just moving average. Just take, and we know that there is seasonability there, and we see a seasonal component. We recognize the period. Okay, we see, okay, D must be this. Then we actually can use this knowledge when we estimate the trend. Okay, we take this local approach. We take this moving average, and then as D is equal to, okay, and D could be either even or odd. Okay, depending on whether it's even or odd, we adjust our procedure slightly. If it's odd, then we simply apply exactly the moving average as it is. Like a D becomes 2Q plus 1. Okay, so we just divide it in two parts. And then it's exactly moving average, where D is equal to 2Q plus 1. If it's actually odd, okay, we have to do something with this because we don't have like xt in the middle, right? And then Q on the left, Q on the right. We don't have that, and then we have to sort of adjust this a little bit. So we just the last ones we sort of give them a weight 1/2, okay? Because we don't have 2Q plus 1, we have 2Q, so we split them in Q and Q, and then we still make 2Q plus 1, okay? But then the last ones are sort of sharing the weight 1, okay? So it's a small adjustment. This is what we can do, and then we just apply this procedure. Once then we can simply estimate the trend m hat. And then we can subtract that estimated trend. So the resulting time series is so-called detrended. Okay, we can detrend time series by subtracting what we estimate. Of course, we still need to do something about this left and right end. Okay, we have to decide how we estimate our trend in those parts. Okay, and then and then we do the following, and then we actually when we detrend it, then we use this detrended time series to estimate the seasonal component. Okay, that's the second step. We simply take all values of this resulting. Where is it? Oh no, this is not S. It should be Y. Okay, it's a mistake here. I did it yesterday. So this must be Y here, the time series itself. So this is just time series. Okay, I will correct that. Let me just skip this. I will explain this by using the example. It's the simplest way to explain this by using the example. So we actually estimate the seasonal component, then we center it. Okay, we compute S tilde. When we center it, we get S hat. okay? And then we extend it, since it must be periodic, then of course, if we estimate it within a period, then everywhere else it's the same. It has to be the same because it's the condition. So then we have our estimator for seasonal component everywhere. And if we have that, then we can deseasonalize. Okay, it's already detrended because we already subtracted the estimator of trend, and then we subtract also the estimator of the seasonal component, and that thing is detrended and deseasonalized. Okay, and we call it E hat. It's sort of like an error, and hopefully that thing is stationary. Okay, so what is here explained is actually realized in the command decompose. That's a standard command in R, and it does exactly that. It actually computes these two components, or three components even. It computes all three of them, like M hat, S hat, and this one, the residual. So it's all done in this decompose. Let me explain how we compute this estimator of seasonal component. Okay, just by looking at this example. So we have a time series which has length 25, and the period is 5. Okay, so there is something like 5 points, and then the pattern repeats itself. Again, 5 points, 5 points, and they all have different colors. Okay, for instance, each first point in each period has a color black. Each second point has color. Sorry, the first one is black, the second one is red, and so on. So how can we estimate the seasonal component within the period? That's all we need, because after that we simply extend it by periodicity. So we take all black points and take an average of those. That will be estimator of S1 tilde. Okay. We take all red points, all second ones, and take an average of those. Okay, so that's exactly what I've written here, but I had to put here not S but Y. Okay, the time series itself. I will correct that. So I will correct it after the lecture immediately. And then we do the same with all blue points, with all green points, and with all orange points. So in doing so, we will get S1 tilde, S2 tilde, and so on, S5 tilde. And then we can center them, okay? From S tilde, we will go to S hat, okay? And then we extend it by periodicity. Once we estimated seasonal component within the period, then we know it just repeats itself. Okay, that's it. This is how this part is done. Okay, this step. Okay, so that would be the thing to do, and it's done actually. Okay, and it's decomposed. To just study this command actually, and you will have to do it, by the way, also in the assignment. So you will see how it works. So that's exactly this procedure is realized by this with this commando. All right. Instead, what you could do, again, if you are not interested in the component itself, you can remove it. And how would you remove it? It's very simple in this case. You simply apply D difference operator. Okay. If you just take xt minus d, then seasonal component will disappear because it repeats itself. Right, it's the same after period D. Then of course it's here. That component is here. That component is here, and they're equal. And you sort of subtract them from each other, and it will disappear. So it's very easy to remove seasonal component by simply applying the difference operator. That's it. Again, it's if you do that, you would think, okay, what about the trend then? The trend may not be removed yet, okay? It is maybe transformed, but it may not be removed yet. But at least seasonal component will be removed. Okay, you can sort of go on and see what you do next about the trend. But seasonal component is very easy to remove in principle. Okay, whatever you do, either like this or by estimating trend and a seasonal component, you can always sort of get something which is sort of detrended and deseasonalized, and then you hope that this thing is stationary. And this is, and then you could sort of apply this. You could model that thing as, for instance, some stationary time series, for instance, ARMA or autoregressive or moving average or a combination of these things. And that's exactly what people do. Okay, that's the field of the. So they sort of remove these things and then they model this and then they apply a field of stationary processes to this reminder. Okay, let's have a look at the examples. Let's remember this US population. Okay, let's just, that thing, to me it looks like exponential, but it also could be a quadratic. Okay, let's just think it's quadratic. And let's just try to model the trend as quadratic function, just a plus bt plus ct squared. Okay, so there is some quadratic function there. So what we need to find is a hat, b hat, c hat. We can do that. That's easy, right? It's just put that in linear regression model, and then you will get estimators, and then you can actually see what this trend does. And it sort of fits pretty good, you see. Okay, what can we do next? We can detrend. If we detrend, then we see, and you see here is nothing, you cannot see anything basically, because it's only in the trend. Trend is sort of prevailing things. You do not see anything, but when you detrend things, okay, there's something, there is some kind of big drop here. Again, that's responsible to this thing. What you see is some kind of irregularity here. And you see that very clearly in the detrended series, and it probably has to do with the war again, I think. And of course, this scale is different, right? So you should understand that this scale is different from that scale. All right. What we can do, we can look at the accidental death time series, right? Remember, we had this seasonality. And we can apply this log 12 difference. Okay, it's just apply this difference of 12 to remove the seasonal component. If we do that and have a look at the result of application of difference operator, we will get this. And clearly there is a trend here. So we removed seasonal component, and then we see that there is a trend. Okay, well, probably next step would be to remove that trend as well. Okay. Okay, here's some sort of very general slide, which is sort of about possibilities. Let me just mention that there are techniques to do all this. Okay, there's just which is called simple exponential smoothing, double exponential smoothing, and triple exponential smoothing. And why I'm mentioning this is the following reason. When I when I sort of supervised a couple of master projects in business analytics, and as people have to deal with some real data, and very often, that was very often the case, that there's some sort of time series there involved, and okay, so what do we do? Let's just try this technique. And there's this very popular technique, simple exponential smoothing, double exponential smoothing, and this triple exponential. We tried that, it never worked. So, I don't know why, but it's still very, very popular. People use that, and actually, let me say that this data set, accidental death time series, is actually can be very well studied by these techniques. Triple exponential smoothing does a very nice job on this real data set. Okay, but the ones I was dealing with, I mean, when people were, doing master projects under my supervision, and then they tried to apply this method that never worked. So, okay, that's just interesting. That's actually pretty good. I mean, it's interesting method. If you see this, it's actually doing what it's doing. It's doing trend estimation. It does trend estimation here. It sort of does trend estimation here as some, and a little bit more than that. It all does some sort of prediction, and here it also does some sort of seasonal estimation in 111. Yes, so it is an extension basically of this moving average. Okay, it's not moving average, it's something else. It's exponential filter, but it has the same flavor. And then here's some sort of what you could do. Okay, you could actually first estimate the trend, then seasonal component, then subtract seasonal component, and then go back to estimating the trend, re-estimate trend, and then re-estimate seasonal component, and so on. You can do lots of things, okay? You can apply different, you can combine all these methods in different sequence. So this is just one possibility here, which people do, yeah. And this comment and this three methods are actually realized by one command only. You can sort of, by option, you could say which one you want. And it's command ETS in the R package forecast. But I was thinking of including this in this course, but I would sort of, that would be too much. So I just wanted to mention that here. All right, let's go to the spectral theory. That's a hard kind of part. That's there are only 2 slides, but there's a lot of information on them. So basically, just 2 slides on spectral theory, but they contain a lot of theory. Okay, it's a big chunk of theory. We're not going to prove anything here, but I'll just mention that once again, it's not part of the exam. Okay, let me say that from the very beginning. Let's just make that clear. But it's part of your assignment. Okay, there is one assignment which is about this, and I really want you to get acquainted with this field, at least have a flavor of that. This is bread and butter of engineers. Okay, this is what they do. Engineers which work in the field of signal processing. This is their field. This is their technique. This is their tools. Okay. Yeah. Let me start with the following. It's a bit heavy material, a bit mathematical, but still. So we have this white noise model, remember? And what we did, we applied some sort of linear transformation of white noise, and we obtained another kind of process, which is sort of a linear transformation of white noise. In fact, we will see in next lecture that this is a special kind of processes which are called moving average. Okay, so this is one particular example of whole family of processes which are all called moving average. We will introduce them formally in the next lecture. We will introduce also autoregressive processes. We will also introduce the combination of these two, which is called ARMA processes, autoregressive and moving average combined together. But at this point, it's just a particular case of moving average. But for now, we don't know that yet. We just say, okay, this is some process, which is just a linear transformation of our white noise process. And we actually computed, we saw that it has a covariance function which doesn't depend on t. And of course, expectation is 0, it's clear. But most importantly, that covariance function doesn't depend on t. So that means it is stationary also. Okay, is it always like that? The question is it always, if we take something stationary, okay, so this zt was stationary, and we transform that in this way, will the result be always stationary or not? Okay, the answer is yes, okay, under conditions. That's exactly what this lemma does. One can prove that lemma, it's not easy, but so let's just start with some stationary time series, not necessarily white noise, okay, some arbitrary time, stationary time, but it must be stationary. Okay, what are we going to do? We are going to transform that, okay? And it's called linear filter. That thing is called linear filter. In the next slide, we will see that formally, this definition. It's not an arbitrary linear filter. It's something which is sort of behaves well. These coefficients Ci, they have to converge up in absolute value. And then we make this infinite, in principle, infinite series here, okay? And then we do that for each t, okay? For each t, it's something, it's basically moving average. Think of that as a moving average, but infinitely. And then the weights are also kind of weird, okay? They don't have to be the same on how one, for instance. So they have to be weights because this series has to converge. So think of those weights. They could be negative, by the way, okay? So they're not really weights, but there's some sort of linear transformation. That's a very general thing you could do, that you could transform your original. This is, and this thing, what it's exactly for engineers, this linear transform is something physical, okay? It's some condensator, I don't know. Well, signal comes in somewhere and it's being transformed, okay? And you could sort of express that as this transformation, okay? For them, these things are also physical things. They're sort of some equipment, whatever. And then you get another signal as a result, so it just comes into some box, something happens, and it goes out, and that's what goes out, okay? And then you would like to know, I gave here as an input stationary, is it stationary as well? Okay, the answer is yes, and here are the characteristics of that thing. First of all, expectation of xt is constant, and it's equal to this number. Okay, that's a number. It doesn't depend on t. You see that? It's a bit difficult number. It's a series of this ct, but it has to exist because this converges here. So it must be something, some number. Okay, and then since it's our original time series was all stationary, so that is the expectation of our original time series. So it gets multiplied by something. Okay, that's fine. But most importantly is the covariance. Okay? The covariance function also doesn't depend on t. It's actually, and you can compute what it is. It's a horrible formula, unfortunately, because in practice, especially if it's infinitely many of them, then it's a double series, okay? That's very hard to compute. But in principle, it is stationary, what comes out, and it has this autocovariance function. That's it. Okay, so you would say fine, but for engineers it's not fine because computing this function is not good. It's just way too hard, and they want some kind of tool. And as this tool was discovered, let me explain this tool. And this tool based on the following, on the notion of spectral density. In fact, people in the spectral theory, they don't work with covariance functions. They actually sort of, they work in terms of so-called spectral densities. For them, it's a more natural notion than covariance function. For us, covariance function, because we started with that, we understand what it is. We know what the covariance function is. We understand the meaning of it. But in this theory, the prime object is actually spectral density. Let me introduce what it is. Okay, let's just assume that this autocovariance function is such that so these are all numbers. Okay, they're indexed by h. H is just integer number from minus infinity plus infinity. So these are a whole bunch of numbers. And then imagine that expectation as the absolute values of this of this infinite sum converges. Okay, that's a some assumption. But once we've done that, then think of these numbers as the Fourier coefficients with respect to the exponential basis. Okay, then we can make a function out of them. So think of them as a Fourier coefficients. So then Fourier coefficient times the basis function. Okay, it's a bit maybe hard, but that the values of that function serve now as a Fourier coefficient with respect to the trigonometric, complex trigonometric Fourier basis. Then we get some function. Okay, that function must be 2 pi periodic, because this is 2 pi periodic. All of them are 2 pi periodic, so that thing has to be 2 pi periodic. It's well defined because of that condition that exists. It does define some function, and that becomes function of this lambda. Okay, and it's 2 pi periodic, and that thing called spectral density. Okay, you would say, so what? So what do I have here? Well, wait, I will come to that. So from covariance function, we can go to the spectral density. Okay, but since these are Fourier coefficients, we can also go back. Okay, now we take that function and compute its Fourier coefficient. Of course, it has to be exactly the Fourier coefficient we started with. So here it's a Fourier transform, and this is Fourier inversion formula. Okay, so it's going back and forth. We can go from covariance function to spectral function, and from spectral function to covariance function. This one-to-one correspondence through this Fourier transformation. Okay, okay. Again, so what? So what did we gain? Okay, what we did gain is this theorem. You will see. Okay, let's just define now the so-called linear filter. Okay, what is linear filter? This is exactly this weights here. Okay, that's called linear filter, and this linear transformation, it's called linear filter of our original time series. You can take any time series and transform it by using this linear filter. Okay, that linear filter is nice. This converges, so this series converges, so that this function exists. Okay, this is so think of those numbers as a Fourier coefficients of some function, and that function is called transfer function. Okay, you can always compute that function if you have those numbers. Okay, well, why not? It's just infinite series. Okay, there it is. You will get that function. It's called transfer function. Now you have your original time series, transform time series. Okay, and now this is the theorem. So now start with stationary time series xt. Okay, and suppose this is a nice filter, linear filter. And suppose we start with stationary time series, and it has spectral density. Because it's stationary, it has autocovariance function. From autocovariance function, we go to spectral density. So this is the spectral density of this x. Then we transform by using this linear filter, our original stationary time series to that one. Okay, that one is also going to be stationary. We know that already. Okay, by this lemma, it has to be stationary, and it also has to have a certain covariance function, which is given by that formula. But that formula is not we cannot use it. Instead, we can actually very easily compute its spectral density. Okay, which is as good as a covariance function. How it can be done? This is the formula. This is actually, again, this is what is bread and butter of engineers. Signal process, working signal process. That's their thing. So you start with the spectral density of your original stationary time series times this transfer function, which comes from the linear filter. Okay, and you take the absolute value, square that, and you will get exactly so you see this formula is very easy. So you can go from here to here very easily. All you need is to just compute this transfer function. And you can always do that because you know your filter. So you just, using your filter, you can compute, you take it as a Fourier coefficient, then you compute transfer function. Okay, once I've computed transfer function, usually, most of the time, of course, engineers, So these are not infinite, they're all finite, okay? All these sums are finite in the practice. So therefore you compute this function exactly what it is. So this is equal to blah, blah, blah. And then once you've computed that, you can compute this also. It's just absolute value squared. Okay, it's by the way, it's all complex numbers. And then you do this multiplication. That's very easy. And then you will get spectral density of this thing. And that's much easier than doing this, okay? So here you have some double summation, but you see it's actually the same. So here it's what engineers, this time spectral theory people, they say, this is, we work in time domain, this is the time domain, and this is the frequency domain. We work in frequencies, okay? So, and for them, it's one-to-one correspondence. You have to sort of, you can bring this to this and other way around. But for them, this is more natural, okay? They actually do all the transformations, all the manipulations in so-called frequency domain. This is working with spectral densities rather than covariance functions. For us, covariance functions is more natural thing than spectral density. You really need to work a little bit longer to get it, sort of to get used to this thing. But again, and so on. There's a lot of this theory goes has a lot of implications, a lot of consequences, and it's very extensive. You could have a look, but that's all we will learn within this course. I think we are done for today. That's it. So if you have any questions, please go ahead and ask. But otherwise, we are done. And next time is going to be the last lecture. Okay, about the assignment, I will put it either today or tomorrow morning at the latest. I'm working on it. It's going to be not as hard as the previous one. I think it will be somewhat lighter, I think. And this whole topic is somewhat lighter, at least to my opinion. Okay, I also will try to finish soon the practice exam. Okay, I'm still sort of thinking how to do the exam because so whether with R or without R, I don't know. I need to do it to decide it quickly, and also the practice exam will be done accordingly. I want to practice exam to be very exactly representative for the actual exam. So I'll have to do it soon. So once you're done, I think maybe 1 week or 2. I think I'll make practice exam so that you could also see what exam is going to be. And there will be practice exam, and there will be some extra examination problems which from the previous year. So there will be enough material to practice in that respect. But I still need to figure out what you will be allowed to do during the exam. I mean, whether because it's still unclear to me what would be the best option. Okay, that's it for today. I mean, so if you have, there are questions. It's all private. Okay. So it was about the what I said at the very beginning about the summary function and ANOVA function. So if, for instance, in this assignment 3, there was this Titanic data set, right? And then there was a factor passenger class, and it had 3 categories. And to draw the conclusion about this factor, you actually had to use ANOVA or drop 1. Okay, so it's not enough to use summary there. because it was exactly the case when you have a factor which consists of more than 2 categories. So okay, so about the assignment, I said assignment, it's kind of, there was a version I discovered that it was open for some time, okay? And maybe some of you actually downloaded a certain version which was open just by mistake. It may be, so it's not the final version, okay? So if some of you already downloaded it, because I can change things. So the final version will be either today or tomorrow morning at latest, okay? Or tomorrow at latest, I will open the assignment 4. And then you will have some time, and it will be more than enough time for to finish the 4th assignment. So this is what concerns the assignment 4. Okay. Yes, the assignment was already uploaded a few days ago. Yes, it was by mistake. It was I made it open by mistake, and probably some people upload, but that may not be the final version, okay? Because I might change things there. Okay, can find the 4th assignment anymore on Canvas. Well, yes, I answered that. So the assignment 4 is going to be, let me put this very clearly, is going to be is going to be open either today or tomorrow at latest. And the one you had is not the final version of the of the 4th assignment, because I made it open just by a mistake myself when I was working on this assignment. It was not supposed to be open, by the way, at that day. So it is supposed to be the start day of this assignment is today. Okay, so I hope I sorted that out, okay, to all of you. So it's not unclear anymore, right? The assignment was already uploaded. Okay, okay, so I answered those questions. I think that's it. We are done for today, and I would like to thank you. So I will be for a little while here. If you have any questions, you can ask them in the chat. Otherwise, I will close this meeting in a minute or so. I had a question, but I had a lot of text. Oh yeah, that's true. Okay, JLM. I think. Well, that's the one. Yes, you JLM. But then you put some. Could I recover the coefficient for it? No, you cannot here because I don't see which comment you used. This JLM. No. You need to apply a comment either ANOVA or drop 1. So I don't see which comment you used here. Oh, it's just JLM. Okay. No. It's not enough. So you cannot recover. It's not a coefficient. Once again, it's the p-value for testing whether a certain reduced model is as good as the big model. So what you so it was privately, there was a question privately sent to me. So I'm answering to that question for those who are wondering what I'm doing here, what I'm explaining. No, that's not good. What that's not enough. So you have to make a JLM first, and then you apply to the result of JLM either ANOVA or drop 1. So that is, or is it good? Let me see. No, it's P. It's a Z value. No, it's not. It has to be chi-squared. So what does he do? I'm not sure. Yes, actually, that's the safest way. So the question is, can we always use ANOVA or drop one for, actually that's the safest way to use because that will always give you the right p-values for testing about the factors themselves as a whole thing. Okay, for continuous variables, it doesn't matter. For continuous variables, you have just one coefficient. So testing for one coefficient is the same as the testing for that predictor as a whole. It's the same thing. But if it's a factor, then there's not just one coefficient, there are a whole bunch of coefficients. So, and then if you're testing for coefficients, it's not the same as testing for the whole factor as a relevant one, because these are different tests. So you really need to make a distinction between these two. And basically what I'm saying, the safest way is simply use always drop one. That's it. If you use drop one, you're always on the safe side. There's everything with all these p-values. Those p-values will be p-values about predictors as a whole thing. Okay, doesn't matter whether continuous or factors. Then all these p-values are the right ones to make conclusions on basis of those. Okay. Okay. I guess that's it. I hope I answered that. Okay, so I'm closing this then. Okay, thanks. Okay, that's it for today. Let me close this session, and then we'll see each other next week. And once again, assignment will be open today or tomorrow at latest. Okay, see you all. Thank you very much.